Hi friends, today we are going to speak about the time period of a spring. For that, I am drawing a spring over here. This is our spring. It is having a spring constant K. There is a mass attached over the spring. Assume that the spring is a massless spring. Then I am going to oscillate the spring by pulling it in this direction. That is, I am applying a force in this direction so that the spring is displaced by a value of x and I'm releasing it. Then the spring will oscillate in this fashion. Then let me write the applied force is Ma. Ma is the applied force. The spring will return back because there will be a restoring force on the spring. As we have learned in our work, power and energy, we know the restoring force will be minus kx. K is the spring constant, x is the displacement. The negative sign is indicating that the displacement is in the, or the restoring force is in the opposite direction of displacement. Therefore, at equilibrium we could write applied force is equal to restoring force. Then I could write Ma is equal to minus kx. We can write Ma is equal to minus kx. Then I am taking this m to the other side. Therefore, A is equal to minus kx by m. I could write it like this. Then let's substitute for acceleration. A is acceleration, and acceleration can be written as d square x by dt square. We could write acceleration like this: d square x by dt square. X is displacement. Acceleration is the second derivative of displacement. Then I could write this equation as d square x by dt square is equal to minus kx by m. This term is taken to the other side. Therefore, d square x by dt square plus k by m into x is equal to 0. Now, we are having a second order differential equation of SH, or we are having a second order differential equation. Then we have studied the standard equation for SHM, that is called as the second order differential equation of SHM, and you might have learned d square x by dt square plus omega square x is equal to 0. This is the second order differential equation of SHM, that is the standard equation for SH. This equation that we have obtained from our spring is like the second order differential equation of SHM. Therefore, we could conclude that spring is executing a simple harmonic motion. Comparing with the two equations, we could see instead of omega square, we are having k by m. Therefore, I could write omega square is equal to k by m. That means omega is equal to root of k by m. Then omega. What's omega? Omega is angular velocity. Angular velocity is having a relation with time period. Angular velocity is 2 pi by t, where t is the time period of the spring that we have to determine. Therefore, I am substituting omega is equal to 2 pi by t into this equation. Then we could write 2 pi by t is equal to root of k by m, from which I could write t by 2 pi is equal to root of reciprocal, that is m by k. Then t is equal to 2 pi root of m by k. This is the mathematical equation for time period of the spring. we have obtained the expression for time period of the spring. It is T is equal to 2 pi root of m by k. M is mass, k is the spring constant. Then if we want to derive an expression for frequency, we know frequency is the reciprocal of time period. Therefore, frequency's expression will be reciprocal of this, that is 1 by 2 pi root of k by m. This is the expression for frequency. Thus, this is how we are deriving the expression for time period and frequency of a oscillating spring. Hope you have understood this.